Hello everyone! Today I will give you a brief introduction to the XGBoost algorithm. This powerful machine learning model has become one of the most popular choices for solving both classification and regression problems due to its speed and accuracy. XGBoost, which stands for Extreme Gradient Boosting, is an advanced implementation of the gradient boosting algorithm. In boosting weak learners, usually simple decision trees, we build sequentially with each tree correcting the errors of the previous one. This process minimizes the overall loss by adjusting the trees iteratively using residuals, which are the errors from the previous models. In a sense, XGBoost focuses on improving the performance of the model by learning from these errors and applying gradient descent to minimize them. At the core of XGBoost are decision trees which serve as base learners. Decision tree splits the dataset based on features to make predictions. However, the trees used in XGBoost are usually shallow because they aim to correct the residuals or errors from previous iteration rather than trying to perfectly classify the data in one go. XGBoost builds these trees in sequence, each designed to improve the shortcomings of the previous one. The sequential construction results in a more accurate and robust model. Now, a major challenge in machine learning is overfitting, where a model learns the noise in the training data rather than the underlying patterns. To combat overfitting, XGBoost uses regulations. It incorporates two types of regulations, L1 lasso and L2 reach, which penalize the model for being overly complex. Additionally, we have the regulations parameters lambda, which adjust the strength of this penalty. XGBoost also includes a learning rate known as eta. The learning rate controls how much influence each new tree has on the final prediction. A smaller learning rate results in better accuracy, but it requires more trees to coverage, which can become functionally expensive. XGBoost optimizes the model using gradient descent. Each tree built in a sequence works to reduce the residual errors from the previous one. The output is calculated by adding the predictions from all trees, with each tree's contribution scaled by the learning rate eta. The formula looks like this. Y final equals the prediction from the first tree plus the learning rate times the prediction from the second tree and so on. This iterative process continues until the residuals are minimized and the overall error is reduced. Essentially, each tree helps bring the model closer to the true output, gradually refining the prediction. Let's now take a closer look at how an XGBoost tree is built. The process starts with a single leaf node which holds the mean value of the target variable. The model then looks at different features and evaluates potential splits by calculating their similarity scores. These splits are computed based on thresholds that minimize homogeneity within the data at each node. If the split improves the model's accuracy, it is accepted. Otherwise, the leaf remains unsplit. Once a split is made, the data is divided into two branches. At this stage, the model calculates the gain of each split to determine how much it improves the predictions. The higher the gain, the better the split. The tree continues to grow until a stopping criterion, such as maximum depth or minimum gain, is met. Additionally, XGBoost applies pruning to stop tree growth when no further splits improve the model. Each tree contribution is scaled by the learning rate, making it an integral part of the tree construction process. Now, let's clarify some key concepts. Similarity score measures how homogeneous the data is within a node. The higher the score, the better prediction. Gain represents the improvement for splitting a node, and we aim for the highest gain possible. Pruning helps prevent overfitting by stopping the tree from growing to depth. Lambda is the regularization term which penalizes overly complex trees. And lastly, the learning rate controls how much each tree contributes to the final output. All these elements work together to make XGBoost the efficient and accurate algorithm. One of XGBoost's greatest strengths is efficiency. It uses sparsity-aware algorithms, which handle missing data without needing to fill or preprocess it. The block structure enables parallel computing, speeding up training significantly. Additionally, XGBoost supports out-of-core computing, meaning it can process data that doesn't fit into memory by loading it in chunks. Pruning also saves computational resources by stopping the tree building process early when further splits don't improve the model. XGBoost is widely used in regression problems where the goal is to predict a continuous target variable. It minimizes loss functions like mean squared error to build trees iteratively to reduce residual errors. Common applications include price prediction and demand forecasting, where small improvements in accuracy can lead to significant business impact. XGBoost is also very effective in classification tasks, where the goal is to predict a categorical variable. The algorithm minimizes the logistic loss function for binary classification or the softmax loss for multi-class classification problems. It iteratively refines its predictions to reduce misclassifications. Use cases include fraud detection, spam filtering, and image classifications. In conclusion, XGBoost is a powerful tool in both regression and classification tasks. Its efficiency, regularization techniques, and iterative approach makes it one of the most reliable machine learning models in use today. Thank you for your attention.